You may find it helpful to download your own copies of these slides that I'm going over here so that you can take your own notes and follow along in that manner. All of these slides that I'm talking about are available as PDF downloads on the D2L site. We're going to start here in Chapter 8, which really revisits a lot of the topics that were first introduced back in Chapter 4 of your textbook. That's when the term nucleophilic substitution was first used, and that is certainly a very common type of chemical reaction in organic chemistry. In Chapter 8, we're just going to talk about a larger variety of such reactions. In Chapter 4, it was mainly alcohols being turned into alkyl halides. In this Chapter 8, the alkyl halides are the starting point to make a number of other compounds by having the halogen being replaced or substituted by other atoms. So you can see this corresponds to what's in the first 11 sections of Chapter 8 in your book. And this next slide here is a general way to talk about substitutions. If you recall, R just stands for any alkyl group, something as simple as methyl or propyl, butyl. It can have rings in it. It can be as simple or as complex as you want. But what we're implying here is that our starting material over here on the left, Rx, would be some alkyl halide. X is commonly used to represent fluorine, chlorine, bromine, or iodine as a typical halogen. And the Y there, Y is not to be taken as the symbol for a particular element. I guess since we've used X already, they're just going in alphabetical order. Y can be a single atom, but it can also be a group of atoms. It's the nucleophile, and that the two dots next to the Y imply that a nucleophile has to have electrons that serve to make the new bond to the carbon in that R group, whatever that is. So nucleophiles make bonds to carbon and provide electrons to do so. And as it says there, it's often the negative ion of an ionic compound that serves as that nucleophile. We'll see a few common examples of that. So in the product side, we've replaced our halogen with whatever Y is, and the halogen leaves as a negative ion, usually not to be collected or further dealt with, but rather the product, RY, whatever that is, that's really what we're going to be interested in. As far as terms, certainly we'll talk a lot about leaving groups or leaving atoms in the case of a halogen. The word nucleophile shows up a lot. And this other buzz term over here, substrate, that's a way to refer to the starting material, in this case the alkyl halides. So we're going to talk about the effect of what particular substrates have on this reaction, how fast it goes. Certainly some nucleophiles are better at doing that than others. Some leaving groups leave quicker and more easily than others. So there's a lot of factors that affect this reaction and how quickly it goes and whether it goes or not. So we're going to sometimes be interested in just predicting the product, but just as often we're going to be comparing examples of substitutions to try to figure out what might predispose one reaction to go more quickly than another. Here are some of the common nucleophiles that you see in Chapter 8. There certainly are more than these, but we can talk about a lot of chemistry with just a handful. And as this slide indicates, the negative ion, the nucleophile, is always going to come from either a sodium or perhaps a potassium salt that contains that nucleophile as the negative charge. So sometimes just the nucleophile, like iodide, may be shown as the reactant. Other times there may be an indication that you're adding sodium iodide or potassium iodide. But in this chapter, the sodium, the positive ions, the potassium, they don't do anything but just kind of go along for the ride. It's that negatively charged ion that we're interested in. Here are three of those in context. Again, the alkyl halide on the left reacting with some negatively charged anion nucleophile, and hydroxide would have a pair of electrons on that oxygen to donate to the cause. That middle one, cyanide, works in a very similar manner. It makes a new carbon-carbon bond. And then finally iodide. Iodide's a good leaving group if it's already a part of a substrate, but iodide is also a good nucleophile, and it can generally replace its other fellow halogens. And in that third case, you see it replacing the chloride. So we're going to talk about, like I say, a number of factors that affect how easily these transformations are. But predicting the products are pretty easy, because if you know the carbon where the halogen starts off, that's generally going to be the carbon that gets a new bond to a nucleophile.